Section 1. Introduction to Distillation and Relative Volatility. Distillation stands as a cornerstone of chemical engineering, playing a crucial role in separating mixtures across various industries. From petroleum refining to pharmaceutical production, the ability to isolate desired components from complex mixtures is paramount. At the heart of this separation process lies a fundamental concept known as relative volatility. This essay aims to demystify the role of relative volatility in multi-component distillation, emphasizing its impact on various aspects of the process. Imagine a mixture of two liquids like water and alcohol. When heated, the more volatile component, in this case alcohol, tends to vaporize more readily. Distillation capitalizes on this difference in volatility, allowing us to separate the components. Relative volatility quantifies this difference, providing a measure of how easily one component separates from another during distillation. The concept of relative volatility is particularly crucial in multi-component distillation, where we deal with mixtures containing more than two components. Understanding and manipulating relative volatility becomes essential for optimizing the separation process. By grasping the principles of relative volatility, engineers can design efficient distillation columns, minimize energy consumption, and achieve desired product purity. Section 2. Understanding relative volatility. Relative volatility, often denoted as alpha, is a measure of the difference in vapor pressures of two components in a mixture at a given temperature. It indicates the ease with which one component can be separated from the other through distillation. Mathematically, it is defined as the ratio of the vapor pressure of the more volatile component, let's call it A, to the vapor pressure of the less volatile component, which we'll call B. So alpha sub AB equals the vapor pressure of A divided by the vapor pressure of B. Here, alpha sub AB is the relative volatility of component A with respect to component B. The vapor pressure of component A is denoted as P sub A, and the vapor pressure of component B is P sub B. A higher relative volatility indicates a greater difference in vapor pressures, making separation easier. Conversely, a lower relative volatility suggests that the components have similar vapor pressures, posing challenges for effective separation. For example, consider a mixture of benzene and toluene. Benzene, being more volatile, has a higher vapor pressure than toluene. The relative volatility of benzene with respect to toluene is greater than 1, signifying that benzene will vaporize more readily. Understanding this concept is fundamental to comprehending the dynamics of the distillation process and its efficiency.